Guess we got started. And thank you everyone for coming today. And will be our final seminar for this semester for the Competition in the House seminar. And we are very, very pleasant to have our very own affiliate faculty, Dr. Josh Warren, joining us. Dr. Warren is an associate professor at the Biostatistical department here, and his research focuses on statistical methods in public health with an emphasis on environmental health problems. And much of his work involves introducing spatial and spatiotemporal models in the Bayesian setting to learn about the association between environmental exposures, such as air pollution and various health outcomes, including the stillbirth that we will hear today. He's also interested in applying and developing some spatial temporal models in collaborative settings, such as the infectious disease epidemiology we have been going through during the COVID-19 pandemic. So without further ado, Josh, the floor is yours. Thank you.
Thank you, Kai, for the introduction. Can everyone hear me?
Yes.
All right, perfect. Yeah, and thanks to Kai for the invitation and Mauro for setting all of this up and allowing me to do this virtually. It's nice to be here talking about something other than COVID. And I guess more recently in my past, I've been doing a lot of infectious disease work. So it's kind of nice to be back into something that I'm still passionate about and still working heavily on. And so hopefully some of this today will be a little bit of review of what we've done and a really current project that we just completed and published. But hopefully there are some elements in here that you can find overlap within your own work. And so if you see something that rings a bell, just please reach out and we can kind of talk. My goal and all of this work is to kind of develop user-friendly methods that are useful for people outside of statistics and biostatistics, so the epi community at large usually. So yeah, just feel free to reach out afterwards and I can share more information. But today we're going to be talking about critical window variable selection for mixtures and particularly air pollution and stillbirth. So we'll go ahead and jump into it. I think probably most people here will know air pollution and reproductive outcomes. There's a pretty substantial literature at this point that suggests exposure to ambient air pollution during pregnancy is associated with a number of adverse birth outcomes, including preterm pregnancy, low birth weight, congenital heart defects, stillbirth, and others. These are some of the main ones. Stillbirth is a more recently kind of emerging outcome of study. Traditionally, it's been preterm birth and low birth weight have gotten a lot of attention. But these associations are stable, robust, and have been observed across a number of different study settings, designs, pollutants, and there are a number of good review papers if you're interested in a lot of the epi literature on this topic. I would kind of summarize a number of the previous epi studies, but as they like to use pollution exposures that are summarized kind of a priori. So they want to focus on a trimester, or they want to focus on the entire pregnancy. Like, what is the exposure across the entire pregnancy? What impact does that have with respect to this outcome? So these are usually pre-specified averaging periods, and they're explored separately in these different, usually kind of traditional statistical models like logistic regression or Poisson if you're using some kind of count model. And so lots of different pollutants are floating around in these analyses, lots of different averaging periods in terms of the relevant exposure period. Luckily, working with pregnancy, we have a relatively stable idea of when exposure potentially affects the fetus. So yeah, so lots of models floating around, lots of pollutants and exposure weeks. But this method is inefficient and doesn't allow for a joint identification of more kind of specific periods across the entire pregnancy in a continuous manner. So more recently, there has been a focus on critical window estimation and identification. So this is where I have done quite a bit of work, I think, in this world. And then even more recently, I would say, and I know a number of people I work with even here at Yale, pollution mixtures are becoming a really big deal. So in this talk, we're trying to combine both of these things that we know really well, or that my group knows really well: critical windows, estimation, identification, and then pollution mixtures, things that we're getting into more and more, it seems. So starting with critical windows of exposure, and exactly what am I talking about when I'm talking about critical windows? So there's an increasing interest in identifying more specific periods of increased vulnerability. Usually we're thinking about pregnancy, but this can go for any really health outcome that you're interested in. But more vulnerable periods of the pregnancy to environmental exposures, and doing this within a single modeling framework. So estimation of these effects we're calling critical windows or windows of susceptibility. The NIEHS included this identification of critical windows as a part of its strategic goals back in 2012. And the focus has remained since then. So understanding like specific timing of exposure with respect to outcome development has a number of features, but importantly, it could lead to improved mechanistic explanations of disease development and ultimately focus guidelines for protection of the unborn child. So we have, like I mentioned, we've done a lot of methods work here, trying to understand variability in these windows essentially, and how to estimate them appropriately. So you'll start to see as I show some pictures, some figures here, that the models become really lots of parameters in these models. So it really becomes an estimation challenge. Like the model makes sense, you can write it down, but can you actually fit these models? So we've done these or considered these models in a number of different settings, including the spatiotemporal setting, survival statistics setting, semi-parametric, non-parametric Bayes with multivariate outcomes, and then more recently, variable selection. And so inference is typically carried out in the Bayesian setting, where I do most of my work, due to increased computational flexibility and, importantly, incorporation of stabilizing prior structure. So not only have these work been done on the method side, where a lot of my time is spent, but I really like seeing them translated to actual practice too. So these methods and kind of variants of these methods has successfully identified these critical windows in a number of outcomes and settings and different populations, but preterm birth, low birth weight, CHDs, so across a number of studies now. So they're getting good traction in other studies as well, not just in the stat literature, which is nice to see. To give you a more kind of practical view of what I'm talking about, this is one of the first studies we published on way back in 2012. And this is for Harris County, Texas, home of Houston, Texas. And on the left two panels, you'll see output from our newly developed method. On the right two panels, you'll see output from more of a naive approach that we were considering at the time. So what we're talking about, these critical windows, are exactly what you're seeing. Maybe you can see my mouse here, but these periods where these risk ratios, in this case, kind of exclude zero, or these risk parameters, they're not on any particular scale that's easy to interpret in this case, unfortunately. But this means that elevated exposure during pregnancy week 10, for example, leads to an increase, in this case was preterm birth, a preterm birth risk. So during your early kind of mid first and early second trimester of pregnancy, we were noticing some interesting elevated risk to PM2.5. And what we've seen across a number of studies now is that these windows vary by pollutant, by outcome. They're very different. There's lots of variability in them. For ozone, for example, it seemed to be early on in the first trimester. So this new methodology allows us to kind of home in on the signal and reduce some of this noise. So if you try to basically imagine your data set, you have lots of pregnant women in your study, and you have linked with that pollution exposure for the first 36 weeks of pregnancy. A really naive thing to do would be, let's just throw all of those into a multiple regression model, some binary regression model, all at the same time. Clearly, there's going to be correlation across time because exposure week 1 looks like exposure week 2, et cetera. And if you do that, you can expect multicollinearity, which is jumping around of point estimates, increased variability, which is exactly what you see here. So our new methodology, which relied on like Gaussian processes and other smoothing techniques, allowed us to, in a data-driven way, kind of tease out signal that you could almost make out by eye here. So if you look hard enough, you can see kind of a similar shape in both cases, but we were able to see a better shape here. So this is what we're generally in the past have been talking about with critical window estimation and identification. Mentioned that we worked on the survival outcome. Well, we started to think about preterm birth instead of just a binary outcome, yes or no. We wanted to consider it as a survival outcome. So what's the probability you make it to week 35 of your pregnancy, given that you've made it to 34, for example? So what this opened up was, well, maybe there are different exposure windows given different outcome weeks. So you can think of outcome week on the x-axis, on the y-axis here, on an exposure week on the y-axis. So if you gave birth at week 27, you only had 27 weeks of exposure, for example. So people were leaving the set as pregnancy happened. And so we introduced methodology that not only kind of smoothed in the exposure direction, but also smoothed across the outcome direction. And so these darker areas indicate weeks and outcome weeks, exposure weeks and outcome weeks, where elevated exposure more adversely impacts like the risk of preterm birth in this case. So there was a distinct difference in this early preterm and then this late preterm, which kind of was impacted by exposures later in the pregnancy. And so underlying all of these kind of simplified plots I'm showing you were these individual outcome week specific critical window plots that we kind of are more accustomed to interpreting. So more recently, we got into the spatial world, noticing that, well, we started noticing that when we applied these methods to different data sets in different areas, we were seeing different shapes, different windows, different pollutants emerging as important. And so we began to think, well, is there spatial variability even at a local scale? And so we developed new methodology that can kind of tease out not only temporal changes in exposure risk, but also spatial variability as well. So there's spatial correlation component here, along with kind of these critical windows floating around as well. So this was 11 counties in North Carolina, including Wake County and the county that housed Charlotte. And this was a low birth weight study. So there's methodology around that can do this. So we were working on these for a number of years, and we got approached basically with a question: how are you actually defining a critical pregnancy window? And it seemed obvious at first, but then we started to really question the assumptions we had been making. But obviously what we had been doing, if I go back a few slides here, is just looking, when do these individual week or time specific parameters exclude the critical value in zero in this case? And we were calling that a critical window. But we started to worry that this might not be getting exactly what we're hoping. Is it capturing the true set? Is this doing a good job? In particular, we were worried about over smoothing with something like a Gaussian process, and specifically with the endpoints. So if you can imagine, I'll go back one more time, sorry to scroll. Imagine the endpoints here and here. We began to worry that the over smoothness could be pulling some of these actually null results into the critical set, or vice versa, kind of pulling some important ones down to the null set. So we were very concerned about the endpoints here when we started working on this more recent work. So our solution to this was critical window variable selection. So we like the smoothness, we like the plots that emerge, we like how we can interpret these things, but a variable selection component would allow us to turn some of these effects off, even if they appear to be significant in the plots. And so what this meant is we introduced like a Bayesian variable selection technique called critical window variable selection, where basically you still have the critical window plots that you know and love and you know how to interpret, but underlying each effect now, you actually have this binary exclusion or inclusion variable that tells you whether this thing should be included, this particular weekly effect should be included in the critical window set. And what we found is that there are a number of times, not in this particular real case study in North Carolina, but through simulation, we noticed that there were times when exactly what we had worried was happening had been happening. So effects near the border here were being pulled into the set, but luckily they were not being included in the variable selection component. So to be in the variable selection set now, you had to have posterior inclusion probability bigger than 0.5, so bigger than this line, and your individual weekly effects had to be exclude zero with a 95% credible interval. So with these two kind of definitions, we were getting a much better kind of recovering the true set of critical windows in simulation, at least. So this really outperformed what we had been doing previously. So we've been moving forward with this variable selection concept since then. All right, so we like critical window variable selection. We like a lot of these other methods. The problem is that, as I know a number of you are aware, the literature has really moved towards, the science has moved towards pollution mixtures and multiple exposures. And a lot of these methodologies were developed with one pollutant in mind. at the most 2 to 3. But they were not generally meant for pollution mixtures, for example. So our goal in this work was to extend what we liked, the CWVS, critical window variable selection, to accommodate mixtures. And so when we started thinking about mixtures, when you have time varying exposures and time varying effects, it became relatively conceptually complicated because you have lots of parameters floating around. So we wanted something that could do like a dimension reduction essentially. So what we thought is a nice solution, like in a single pollutant context, or I'm sorry, in a single exposure time period context, is this weighted quantile sum regression, which I know a lot of you are familiar with because I've helped write pieces of grants that have discussed weighted quantile sum regression here. But it offers a nice interpretable solution for estimating the impact of a mixture on an outcome. And it has this really nice sum to one constraint on the regression parameters. And so you get, in the end, you have 20 pollutants, for example, and you get to see the relative contribution of each of these pollutants in terms of the entire mixture. So you have these little sum to one between 0 and 1 probabilities or proportions that describe the role of individual pollutants. And then you have this global regression parameter that describes the impact of that mixture as defined by those weights on the health outcome. So it does a little two-stage process to estimate weights and then global regression parameter, not important for this talk. More recently in 2020, this was extended to the lagged weighted quantile sum regression. And yeah, it extended WQS to the multiple pollutant setting in a really, I think of it as a relatively ad hoc solution, but basically WQS is fit at each exposure week separately. The weights are estimated, the mixtures are combined based on those weights, and then those kind of packaged mixtures are thrown into like a distributed lag model to estimate similar curves as what I've been showing you so far. So the estimation of the weights and their relative importance in the mixture are done separately outside of kind of the estimation of the regression parameters as well. So this, more of a two-stage approach. All right, so we like WQS because of its relative simplicity and its interpretability. We like critical window variable selection. So the goals here were to combine that estimation identification ability of CWVS with the interpretability and shrinkage properties of WQS within a unified modeling framework. And extending, so WQS is nice. It has these sum to one components that are between 0 and 1. But you don't actually get a sense of variable selection when doing this. So none of the weights can exactly equal 0. We wanted a more sparse solution. And so we introduced also a way to make these weights exactly 0. So you can get a better sense of which pollutants are the main players in the mixture. And so what we're calling this is CWVS for mixtures, or CWVS mix. And so some features before we get into a little bit of the details of the model, these are like just if you take nothing else away from like what this model does, this is, I think, the important slide here, is that we have main effects and first order interactions between the pollutants during each exposure period. So week 1 of pregnancy, week 2 of pregnancy, all of these interactions, all of these main effects are included. So there's lots of parameters you can already imagine are floating around here. We still hold on to this sum to one mixture weights at each exposure week separately, but we want to account for the fact that what's happening in exposure week 1 may be similar to exposure week 2 to 3 to 4, with this correlation dying out as you get further apart in exposure time. So we want these weights not to have to be estimated kind of independently at each exposure week. We want to enforce some smoothness, data-driven smoothness, preferably, to estimate these weights. And as I mentioned, we want these weights to have a variable selection component so we can actually identify individual elements of the mixture. And we still have this global risk parameter, and this is going to follow the CWVS model so that we can estimate these critical windows more accurately. All right, so the goals of this study, before we jump into some of the methodology here, is to develop CWVS mix, as I mentioned. Simulation is really important in this world. I want to make sure that what we're doing is not just duplicating other efforts and that it's actually offering something new, something helpful to the literature that we can point to. I think I know the shortcomings of something like lagged weighted quantile sum regression, but until I see it actually happen in simulation, it's just kind of hypothetical. So finally, we want to investigate the impact using this new methodology of multiple ambient air pollutants on stillbirth risk. And in this case, we're focusing on New Jersey from 2005 to 2014. And actually, we have really nice output from a novel data fusion model. There are lots of data fusion models floating around right now, but this is one from 2019 from our collaborators at Georgia Tech and at Emory that provided 12 pollutants, 12-kilometer grid cell size across the entire US, daily, no missingness, things like that. So for these particular pollutants. All right, so let's talk a little bit about the model and what it does and some of the intuitive features that I think it has and why it might work well. So yeah, we're starting with some outcome. It could be some adverse health outcome like preterm pregnancy or not, or stillbirth or not, some Bernoulli outcome, where this PI describes kind of the probability that person I experiences this outcome. We model this probability using logistic regression as we normally would. These green, I'm kind of trying to keep people's attention to the parameters and how I'm mentally grouping them as well. So these green represent these typical like demographics. We know there are certain risk factors for different health outcomes, particularly pregnancy outcomes, being over 35, for example, with preterm pregnancy, alcohol, smoking, et cetera. So this would go into this XI transpose beta, this vector here. Where a lot of our work came in are on these blue parameters, which are the weights that I've been talking about. So these weights, these blue parameters, actually sum to 1 at each exposure week. So at each exposure week T, we basically have a vector of lambdas that are weights between 0 and 1, could be actually equal to 0 exactly, and they sum to 1 at each exposure week separately. You notice they're indexed by T because we're allowing the possibility that the exposure profile changes across the pregnancy. So early on in the pregnancy, maybe the risk is primarily driven by pollutant A, but later on in the pregnancy, perhaps that shifts. And so the weights would shift as well. But we expect this shift to be smoother rather than complete choppiness across the exposure weeks. And so what these weights do are they kind of multiply here with the main effects and these first order interactions. And if you think about taking this sum across main effects and interactions, you have this package of weighted exposure essentially. And the alpha here tells us whether at exposure period T, this package has any impact on your ultimate probability of developing the outcome. So we have this nice sense of the weights help us describe what's happening with the mixture profiles, but the alpha keeps us honest and keeps us able to say, well, you know, this mixture is interesting, but it has no impact on the health outcome of interest here. Yeah. So how do we do these mixture weights? As I mentioned, 2 features that we're interested in, the ability to actually equal 0 and smoothness across time. And so first point is we introduce these latent weight parameters that I'm calling lambda star. Don't get too caught up in them. Basically, they're continuously varying parameters that as soon as they cross the 0 threshold, they turn on in our model. So that's what this maximum is doing. So they turn on and they give you some weight. And then as soon as they cross into negative territory, they go to 0. So this is how we're getting actual zeros in these weights. So the lambdas and the lambda tildes can actually equal 0 based on these underlying latent weight parameters. All right, so we keep them summing to 1 by dividing by the sum of the numerators essentially. So whatever weights are positive get summed, and we're basically self kind of correcting here so that the weights always sum to 1, these weights combined. For the interactions, we don't want the case, we prefer a sparse model, particularly as the number of pollutants get really large, so the number of interactions will grow. So what we want are interactions that are only turned on essentially when the main effects are turned on. So you can see these 2 indicators I've added basically say if the main effect themselves aren't both turned on, this interaction effect gets zeroed out already. So the interaction has a kind of a higher bar to clear, this strict hierarchy, basically where both main effects have to be on and the interaction latent variable has to be on. So there's the 0 component. Now, how do we do smoothness across time? Well, it's all about this correlation structure. So these latent lambda star parameters that control the weights are actually modeled as a multivariate Gaussian process. And I think the key thing to focus on here is that there's this underlying correlation structure that tells us as two exposure time points get further apart, this exponential of a negative number will get closer to 0. So correlation dies out as exposure time gets further apart. Now, as they get closer together, this correlation is going to be higher. And the main parameter that controls this level of correlation is this phi parameter. And we actually put prior distributions on this to allow the data to drive the inference rather than like our view of what we expect this smoothness to look like. So yeah, this is data-driven kind of smoothness across exposure time. All right, so we've got the weights handled. They have both properties that we care about. Now let's talk about the mixture impact itself. So this alpha, recall, tells us whether the mixture that we observe at time point t, or that we estimate at exposure time point t, is actually relevant to the health outcome. So we want this variable selection here because we've noticed the problem with the endpoints that I described earlier. So to do this, we decompose this effect into two pieces, a continuously varying piece and then this binary piece that I mentioned earlier on in the talk. The binary piece are just independent Bernoulli random variables, but we imagine that if you're in the critical window set at time 1, then you may be in it at time 2 and may be more likely to be in at time 3. So there may be a sense of correlation across exposure time here as well. So while we model these things as independent, the probabilities that underlie these 0 and 1 variables are actually smoothly varying and correlated across time. So again, we use this kind of exponential correlation structure. We allow for cross correlation between the continuous and the binary piece. Not important to get into here. You can kind of read back over. I can share a paper with you if you want to, or talk more about it offline. But essentially, there's some cross correlation, there's correlation across time, but this allows for smoothness in the effects, in the kind of the regression parameter effects that we've been looking at, but also in the variable selection as well. And both of these things come together to kind of define the critical window variable selection model. To finish the model, recall everything's in the Bayes setting. So really weakly informative prior distributions, kind of standard prior distributions when possible. Nothing too interesting here. So the model you may be looking at on this previous slide and thinking there's a lot of parameters floating around here. There's a lot of output that you're going to be estimating. So how do you make sense of this as a practitioner, someone who actually wants to know if a mixture is having an impact on your health? Well, luckily, we still have relatively nice and estimable kind of effects here, associations that we can talk about. So for example, for a change in the log odds for a 1 unit increase in each pollutant during a particular exposure period, this would be the quantity that you would make inference on. So you would exponentiate this and you would have like an odds ratio, for example. Now recall for any model that includes interactions, the interpretation is always increasingly complicated because it matters where you start when you have interactions. So if you're already at a high level, so the values themselves of exposure have to come into play. But nonetheless, you can still get nice quantities to estimate in the end. And if you're only interested in what happens if pollutant A increased during exposure period T, you can write down actually what that looks like as well. So you can estimate both of these things relatively easily from our output from our model. All right, so we have a model that kind of checked all the boxes, at least in my head when I was writing it down, and I tested it, we can fit it. It seems to work in that it's converging and it's producing things that look reasonable. But the simulation study really allows us to dig deeper and say, is there anything, it's obviously new, but is there anything beneficial to what we're doing, or should we just be doing something simpler that already exists? So we wanted particularly to ask, how does CWVS mix compare to some of these existing approaches for 3 different factors that we're interested in? So first, identifying the true critical window set. Obviously, probably the most important part of critical window research here is like, let's get the critical window set right when we're estimating and identifying these parameters. But obviously, when you're talking about mixtures, we also care about these weights, right? We want to know that the mixture profile we're looking at on a certain exposure period actually is, reflective of the true mixture profile that makes sense here. So how well do we do at estimating these lambdas and lambda tilde parameters that describe the effects of main effects and interactions? And then finally, how well do we do at estimating the magnitude of risk? So these alpha T parameters, we want to make sure we're getting these right as well. And as a side issue, I guess, just more out of our curiosity, how well does this variable selection process work for the weights that we've introduced? So now we need to think about what are competing methods in this space. There aren't a lot of methods out there that aim to estimate critical windows with time varying exposures and multiple pollutants. And the ones that are out there give different enough output that it's hard to compare one model to the next. But here are 3 approaches that we kind of came up with. One is the most naive, kind of where I would always start as a practitioner with a new data set, this equal weights approach. So maybe just averaging all of the exposures for a person on a given exposure week and including that average and the interactions with the other exposure periods in a framework, a distributed lag framework. This is called equal weights, or EW. A PCA approach also makes sense. So let's allow the data to determine the correct weights, or these lambdas, but let's focus it only on the exposure period, only on the exposure data. So at each exposure period, fit a PCA to the person-specific exposures and generate these weights that kind of describe the relative contribution of the different interactions and main effects in the mixture, and then weight the mixtures in that way and throw that weighted value into the distributed lag regression model. So for all of these methods, we're using the original CWVS so that we're comparable, so that the results are actually comparable across. And the only thing that is changing essentially is how we define the weights. And then finally, the most sophisticated approach at that time was this lag weighted quantile sum regression that we talked a little bit about, where we applied weighted quantile sum regression separately to each exposure period, let that estimate the weights, create the little package of exposure, and then throw those packages into the regression model using CWVS. So once you have the weights, like once you condition on the weights and you know the weights, you basically have one exposure, and that exposure is the package, the mixture package that you've made. So the modeling becomes much simpler in that case. So how did we go about to test these different methods? Well, we started very simply. So these represent the weights across exposure period. In this case, I'm pretending like there's only 5 weeks in the exposure set. In reality, I let that vary for each data set. The length and the start time of the exposure window changed. But for this case, we assumed it started at pregnancy week 1 and went to week 5. And so in the simplest case, we just assumed there was one pollutant at play and it stayed constant across the exposure period. This is really simple. One pollutant is driving the entire risk that we're seeing. In another setting, we assumed that there were 2, but there was no changes over time. They were always static across time. In 3, there were 3 that were coming into play. At 4, and then 5 of them. Obviously, as more come online and become important players in the mixture, the weights generally go down because lots of these have to be non-zero. In setting B, we wanted to allow for some variability among the important pollutants. So we still allowed for the same important pollutants to be important at each exposure period, but we allowed their relative contribution to change across time. So early on in pregnancy, this one was important, but then its contribution went down and it was kind of surpassed by number 2 here, pollutant 2, and then they can keep swapping in and out across the exposure. In setting C, it was complete chaos essentially. Different pollutants could come online and then leave and become important or non-important, go to 0. We don't anticipate this would be the case, but it would be nice to know if our model can somehow collapse and kind of accommodate this wild behavior, I guess. So yeah, this is something that kind of testing the extreme of all these methods is what we were trying to do here. So we'll jump right into the results just to give you a sense of what happened when we tested these models with lots of simulated data sets. CWVS mix continuously and kind of consistently was able to get the critical window set more accurately than the other methods. which struggled kind of in varying degrees across these different settings. In terms of estimating the weight parameters, there's a generally, CWVS mix has a lower mean squared error, so it's doing a better job of estimating these parameters. As you would expect, like with equal weights, if you assume each pollutant and interaction is playing an equal part in the story, you can be very bad off a lot of times, which is why these weights or these values are so high for some of these methods. And finally, with the estimation of the regression parameters that describe the magnitude of risk, generally we're seeing improved performance with CWVS mix. But interestingly, at least at the time when we first saw this, is that the equal weights method does a pretty good job of estimating these risk magnitude parameters as the number of important pollutants increases. So if you tell me that every one of your pollutants are important, then it's going to be hard to beat something that gives all of the pollutants equal weight. So that's kind of the intuition behind it. As more pollutants become important, giving everything equal weight is not such a bad idea. It's just averaging away some of that error. But generally, we're still doing well, and specifically in comparison to the lag-weighted quantile sum regression. That's really importantly, because at the time this was the kind of the main method out there that aimed to do the same thing we were doing. So in summary here with the simulation study, we did really well in critical in terms of accuracy, weight parameter estimation, and even in the risk magnitude parameter estimation. So models that don't actually estimate weights are more efficient when the complexity or the number of important pollutants grow. And a little bit about the variable selection that we introduced with these latent variables. It appeared to do really well, again, as the number of important pollutants was relatively small. So if you have lots of pollutants that are important and their interactions are important, it was hard for the variable selection process to kind of tease out when something's included or excluded. It tended to just say everything was included. So something to keep in mind, I guess, as a limitation perhaps of this approach. All right, so now on to the real data application that we had. And this is part of a larger kind of climate change, heat, preterm birth study. We collected lots of state-specific data, birth records for all the way back to 1990 for maybe 12, 14 states. And so this one was set in New Jersey, but we focused on stillbirth, given their really strong stillbirth data collection kind of methodology that New Jersey was using. So stillbirth, the death or loss of a baby at least 20 weeks of pregnancy, affects about 1 in 160 births in the US. There are some known maternal risk factors, Black, mother, 35 years age or more of age, low SES, smoking, etc. And recent literature review meta-analyses suggest that PM 2.5, CO, and O3 are associated with increased risk. This was really recent, but that more studies are definitely needed. There's not a lot, as in comparison to some of the other adverse birth outcomes. There's not as much done with stillbirth, at least. However, a majority of these previous studies have focused on, again, single pollutant approaches, wide exposure periods like the entire relevant pregnancy before the delivery. So there is a need for kind of multiple pollutant critical window methods in this setting. So this is what kind of made us think about developing this methodology, but also applying it in this case study. So a little bit about the data we had access to. We had live birth and fetal death records from New Jersey from 2005 to 14. We included singletons with gestational age of at least 20 weeks, no birth defects, conception date in 2005 to 2013. We ran a case control analysis here where 5 live births were linked with each stillbirth, matching only on race, ethnicity. And we actually ended up running these analyses separately for each group: non-Hispanic Black, non-Hispanic White, and Hispanic. And in terms of what our exposures, we included weekly pollution exposures through gestational week 20 were included in this analysis. All right, a little bit about the pollutants. I mentioned we relied on a data fusion model that gave us kind of fine scale, spatially and temporally estimates of 12 pollutants. across New Jersey, across the US actually, but focusing here on New Jersey. So you can see the pollutants listed here. And we linked each woman's residence at delivery with the closest grid cell where data were available or the estimates and predictions were available, and assigned weekly exposures across the first 20 weeks of gestation. I know there's always a lot of pushback in these birth records because we don't have residential mobility. We don't have sense of like how often people move, and we know moving is differentiable by socioeconomic status, for example. There are a lot of factors that influence moving during pregnancy. But if maybe this will make you feel somewhat better, but we did a study in 2019 to kind of assess the robustness of these critical window methods more generally to lots of different sources of error, including residential mobility. And the results were actually very promising, I thought. So the findings are robust generally to kind of this exposure misclassification or exposure error that's introduced through mobility. All right, so in summary, I guess for the data, we had around 1,300 non-Hispanic Black stillbirths in this time, 928 Hispanic, and 1,100 non-Hispanic White. Our covariates that we included were year of conception, season of conception to control for this kind of seasonality and long-term time trends and pollution exposure, tobacco use indicator, age category, education. We had the sex of the fetus. And to control for spatial kind of residual correlation, we actually included latitude, longitude of the residents at delivery and their interaction term. As a pre-screening, because we had 12 pollutants to work with, we didn't want to introduce a lot of noise, if possible, into the new framework. So we did a pre-run of the original critical window variable selection on each pollutant individually, as most analyses would do anyway, and identified a subset across all of the different data sets. And by different data sets, I mean the non-Hispanic Black, non-Hispanic White, and Hispanic. So all of the relevant kind of significant exposures that came up during any exposure period were included as a subset into this bigger framework. And so in total, we had PM2.5, sulfate, nitrogen oxides, ammonium, and nitrate that kind of made this pre-screening period into the final subset. All right, so here is some of the output that we thought was interesting. You know, there's a lot of output that can be shown, as you already know, I guess now. There's weights at each exposure period, there's regression parameters, there's just a lot that can happen here, and there's interactions, there's main effects. But first, let's focus on the first column here. And this is at least something we can hold on to that we understand from previous work in this space. So what we can see for the non-Hispanic Black population that we were working with in New Jersey during this time, that elevated exposure, I'm not going to say to what yet, but elevated exposure to some combination of these 5 pollutants during pregnancy week 2, and then later on in the pregnancy 16, 17, and 20, actually led to increased odds. So these are odds ratios being presented of stillbirth. And so we can kind of take these in and say, we get a sense of the critical windows that are identified. We also get a sense of the variable selection component that I mentioned. And in this case, they line up pretty perfectly. These are consistently in the model, actually included in the Bayesian variable selection model, but also when they are in the model, they're positive. So this risk is in the right direction. So more pollution during these pregnancy windows, more risk of stillbirth in this population. Now the question becomes, well, what are you talking about when you talk about the exposure? Like, what is the mixture that you're talking about in week 2, for example? Because we have 5 pollutants and their interactions floating around. So focusing first, so now let's move to the second column. This represents the interactions, this top part, and the bottom part represents, this is main effects, and the bottom part represents interactions. So you can see ammonium is playing a big role throughout until week 16, which is dominated sharply by nitrogen oxides, and then ammonium comes back into play here. In terms of the interactions that are important, it looks like PM2.5 and ammonium early on, and then later on it's nitrogen oxides and ammonium kind of come into play. So a lot of this is noise. I did not show you the variable selection component, but it probably would be nice to kind of gray these out if they're not selected in the model. But a lot of these actually are selected in the model with our variable selection. So while these look to be non-zero weights, some of them are actually exactly zero, essentially, because of the variable selection component. but there's so much output, it's hard to figure out what exactly to show in a digestible way. So this is where we landed. So, interesting results. You get to see how the exposure, kind of the mixture transitions across exposure time. You get to see what impact that has on the actual risk of the outcome that you're talking about. So a nice, I think, coherent story can be told. If you're picturing your own analysis here, you get to talk about the risk overall to the mixture kind of combination or profile, but also then dig deeper into individual weeks and talk about which ones are important, which interactions are important, for example. For the non-Hispanic white, there was very little indication that these pollutants were playing a role, I guess, in the kind of development of stillbirth or the risk of stillbirth in this population. And for the Hispanic population, it looked like there potentially was some uptick here at the end, but nothing significantly jumped out either. And so at this point, it's almost you don't start to investigate and overinterpret these weight parameters, given that you're not seeing anything here. So I kind of consider this to be noise, essentially, for the Hispanic and non-Hispanic white results, for example. So a little brief kind of wrapping up here, summary of our findings is that for the non-Hispanic Black data set and variable selection results, PM2.5 and its chemical constituents are primary drivers of risk. And this was actually changing across exposure week. So driven in week 2 by a lot of interactions and kind of individual pieces. Week 16, mainly heavily driven by nitrogen oxides. And then week 17, 1 or 2 pollutants and their interactions. So all the other interactions that are not listed here among the 5 variables were actually not significantly important here. So nothing seen for the non-Hispanic white and Hispanic populations. And I guess in conclusion, we introduced CWVS mix, which combines smooth Bayesian variable selection in the weights and the regression parameters with interpretable weighted quantile sum regression shrinkage to identify critical windows, but also kind of understand and kind of dig deeper into the mixture itself. And importantly, at least from our perspective, is that CWVS mix seemed to offer something that the existing methods didn't, so consistently outperforming these other methods for identifying the true critical window set, estimating weight parameters, which is really important for interpreting the mixtures, and then estimating the risk magnitude parameters as well. And our stillbirth results from New Jersey were in qualitative agreement with those in the literature, in that PM2.5 consistent signal across many studies, while developing, kind of gaining new insights regarding the exposure timing in this particular study. Obviously, more work is needed. And so I guess before jumping to this, we were working on extending this framework. So I'm working with the group at Emory here on extending this framework to allow the windows themselves to vary by something like socioeconomic status or race ethnicity or other individual level factors. So there's this effect modification floating around now, plus the mixtures. So it's becoming a really big task to kind of do all of this in a single framework, but we're trying to take baby steps essentially. We like where we're at now. We think it works well. It's robust. It fits well. And can we extend it next to the questions that are being asked? So again, if you're someone who is asking similar questions, please, we can talk. And I really enjoy sitting down with collaborators and trying to develop new methods that can answer the questions that they have. But if you find that your setting can already be answered by some of these methods that I've discussed today, on my website and on my GitHub site, I keep a lot of these packages that I've created with help documentation, and then you're always free to reach out to me as well. But if you're looking to do this original Gaussian process critical window estimation, we have a package for that. Howard Chang at Emory, go through my website again, you'll find this survival version of the model up there as well. CWVS in its original form is there for download. The spatial version, which hopefully we're thinking about extending in soon to account for something like oxidative potential of these pollutants, that's also there. And then the newly developed methodology is also there for download and for use as well. And this obviously could not have happened without collaborators, including Howard at Chang at Emory, Lauren at RTI, did a lot of data management, Matthew Strickland and his Lindsay at University of Nevada, Reno, and then James for providing the or helping with the data fusion output as well. And here are this grant support here that I mentioned: extreme heat duration, and then data integration methods for environmental exposures. So yeah, please feel free to reach out if you have any questions. This work that I went over today is in press at Annals of Applied Statistics. Not on their website yet, but should be really soon. But I think there's a version on archive if you're interested, or if you want the most up-to-date version. I actually think I sent it to Mauro, who may have passed it out to the class. But yeah, definitely feel free to reach out if there are any questions or anything I can help with. Yeah, that's it.
Thank you so much. Our students were impressed with this heavily quantitative focused lecture. And we already collect some questions from our students already. But for folks who are joining online, if you do have questions, please feel free to put in the chat box. So the first question, one of the students is observing that in your study, you found the elevated risk was found in week 2 of the pregnancy, which is very early. So perhaps many pregnant women are not aware of the pregnancy at that time. So in terms of the intervention at this early stage of pregnancy, what's the kind of policy implications of your finding?
No, that's a really great point, and this is something we haven't figured out how to deal with either, but we've run into a number of interesting results that we've seen early in the pregnancy. We've seen protective effects at some points for like PM2.5 exposure and preterm pregnancy very early on in the pregnancy, and we believe it could be due to exactly what we're talking about, people who don't actually know they're pregnant at that point. And so miscarriage is an issue that isn't well kind of documented by a lot of these states. There could be just fetal loss in general that we're not capturing in the birth records. And so there's this population that we're not even including in a lot of our analyses that are lurking around and kind of could be biasing some of these early week results. In terms of policy implications, yeah, it's a really good question. I don't know, other than I guess if you're trying to get pregnant, if you know you're in that stage, I mean, maybe it's helpful for you. But if you're someone who doesn't know, unanticipated, yeah, there's only so much that can go into outside of just cleaner air altogether, right? Which is something everyone can kind of agree on. But yeah, I think it may only affect a subset of people who are either attempting to get pregnant or kind of really regimented and like know their schedule, for example. But yeah, there's this whole other issue about people who aren't in our data set. That's a really great point, and we have not figured out how to solve that yet.
Yeah, tough question. Thanks, Josh. We do have another question from actually 2 students read this. They really appreciate your talk about this new matrix, and we realize this is the package. Our package is available from your GitHub website. So anyone who's interested in applying that, you can download the R package and run. But the students are wondering, like, beyond these time-varying air pollution mixtures, there are a lot of other mixtures in terms of environmental exposure, like temperature, green space, other things. So how does your approach, the CVWS mix, apply to a broader setting of environmental exposures?
I think my push, and if you read the paper, you'll notice that I really push for people to think about that in their own setting, because I think it's generally applicable to it doesn't have to be a pregnancy outcome. It doesn't have to be air pollution. What it does have to be is consistently measured across some exposure period. So I'll often get questions that, I have 2 time periods measured, in the first trimester and then in the third trimester. Can I fit your methodology? No, well, we need more fine-grained exposure information that's consistent across the individuals in order to estimate these critical windows. So I think the only barrier for entry is that you have consistently estimated kind of exposures for the population of interest. It doesn't matter so much what the exposure is. Now, I say that, but if you're bringing binary exposures and you have limit of detection issues, there are obviously some issues that will need to be sorted out. but the framework itself should work really well. The other caveat is you'll notice that a lot of my work has been focused on pregnancy outcomes, and that's because the exposure period is so well defined. If you're working with something like cancer, for example, well, how far do you extend back in time the exposures? Like how you could go years and years back. So there's this cumulative idea as well that's really hard to understand. And these distributed lag models are great as long as you can a priori tell me what the relevant exposure period is. I can tell you if any of the interior parts of that exposure period are important. But if you're telling me you don't know when the exposure period potentially started, it's a completely different conversation. So your outcome has to have, or preferably would have, some type of relevant exposure period. It's actually even better for something like cardiac heart defects, which we know the heart forms between like weeks 3 and 8 of pregnancy. So you can really focus in on something like daily or even sub-daily if you had that type of exposure information. So yeah, those are the two. Generally it should work, but just make sure you have a good sense of the exposure period.
Very good point. Thanks, Josh. We do have one comment from our online audience. So I'll read, Dr. Warren, could you please share your thoughts on applying the critical window analysis with count data?
Sorry, with what? With
count data. Yes.
Yeah, so that's a really great point. So I'm actually on sabbatical right now, which is why I couldn't be there in person with you guys. But over the sabbatical, I've developed the framework and the code to account for binary outcomes, continuous outcomes, and count outcomes as well. Luckily, if you've taken my Bayesian course or you're going to take it next fall, you'll see how all of these connect and lend themselves really nicely to kind of full conditional distribution updates that make the model fitting process really kind of slick and nice. So we have a negative binomial regression, for example, that can do the same thing. You just have count outcome data, or we have if you have a continuous measure, for example. So I'm really aiming this. I hope this method doesn't just pop up and then disappear. I want people to use it. I want it to be useful. And so that's why I'm trying to extend it and trying to get people to use it in different contexts. So yeah, definitely. I love those types of questions.
Thanks, Josh. Because we actually have another the Biostatistics class right after this, so we have to end early, and we do have a lot of students and questions, and I'm sure they will contact you for those who want. So perfect. Thanks again, Josh, for this wonderful talk.
No, yeah, thanks for being here.